This is the last session for panel data and also last session for your semester 2 class. And as you are roughly 230 in number, and of course all of you cannot participate in the class directly in a Zoom because there are some limitations in Zoom, you know. For that reason, I have provided the recorded version of the class in the YouTube channel. So who are not joining the class or who cannot join the class, they can also have the access for the class if they want to have. So you can follow the YouTube channel, or I have also uploaded the recorded versions in the Facebook because many of you are familiar with Facebook and you are connected with the Facebook. For that reasons, I have put these recorded versions of the class in the Facebook, as you can get access, particularly those who cannot attend the class directly, so they can also get the full benefit of the class. And you cannot blame later on that, sir, we don't know what you are teaching and we don't know which part is covered in. So you cannot say further. So for that reasons, I have trying to keep the recorded part of the class in the Facebook, in the YouTube channel, so you can go through them as well, particularly who are not present now. Okay, so let me continue. So the error component model, we are discussing about the error component model. Error component model appears when the error, random error, is decomposed into two or more parts. You will get an error component model. So how do we decompose the error? One way to decompose the error in this manner: total error is decomposed into two parts. The second part is purely random, epsilon it, and the first part is unobserved and varies across the cross-section area. In the second formulation, again, the second part is the purely random and the first part is unobserved over time period. So what is the justification for decomposing the total error in this way? Suppose we are estimating a Bayes regression model. We have provided this classic example earlier as well, the Bayes regression model. So if you are familiar with the theory of human capital in labor economics, in the theory of human capital, we have wage rate a person, a worker can get depends on so many factors, and among them the major factors are the level of education. So suppose in this regression model, Y denotes wage rate, X denotes level of education, and U incorporates all other factors affecting wage rate other than level of education. Okay, so in this random variable or the random error, one component may be the level of intelligence of the worker, and the level of intelligence of the worker is unobserved. Unobserved in that sense, we don't have any information, we don't have any data. So in your sample, you don't have any information on the level of intelligence of the worker. So level of intelligence is incorporated into this random error. Okay, and X is the level of education. So how do you face a endogeneity problem? You can easily understand. So within you have level of intelligence, and X denotes level of education, and it is easily understandable. The level of education will be highly related to the level of intelligence, and the level of intelligence is a component of U. As a result, the level of education X is correlated with the error term U, and you have to face the problem of endogeneity. So to remove this endogeneity, if we can separate out that part of the error which is responsible for endogeneity. For example, suppose we are separating out the level of intelligence of the workers, which are responsible for the heterogeneity across the worker. One worker is different from another worker because of the level of intelligence, for example, or the level of efficiency, whatever may be. So level of efficiency, level of intelligence, which are incorporated in the random error, and X is the regressors. And in human capital theory, the major regressor is the level of education, and level of education is directly related to the level of intelligence. So we can say X and U are highly correlated, and you have to face an endogeneity problem. Now let we decompose UIT in this manner. UIT is equal to mu I plus epsilon IT. Suppose mu IT denotes the level of intelligence of the cross-section unit I. So here we are considering worker, a particular worker as a cross-section unit. So mu I denotes the level of intelligence of a particular worker, and we are using the suffix I only, not T, simply because the level of intelligence of a worker may be different for different workers, but this level of intelligence may not be different over time, at least for a shorter period of time. So over time, the level of intelligence of a person, the level of intelligence of a worker may not be different, but the level of intelligence may be different for different types of worker. So in a Bayes regression equation, the random error UIT may be decomposed in this way. So if we take mu I as a separate from UIT, so it is a component of UIT. So we just separate in a simple additive form mu I plus epsilon IT. So this epsilon IT does not capture the level of intelligence now because we are separating out. So after separating out, epsilon IT will be will not be correlated to X. So you can eliminate the endogeneity problem. Okay. In the second formulation, we are considering the unobserved heterogeneity over time. So when this kind of model will be applicable, suppose we are estimating a production function, Cobb-Douglas kind of production function. So Y is a dependent variable, X incorporates labor, capital, etc. So along with labor and capital, there are so many factors that can affect the level of production of a factory unit. And one important factor relates to the technological development. So technology using different factory units are different. For that reason, the level of production may be different for different factory units using the similar kind of labor and capital. So total output Y may be different for a given set of X simply because the different technological parameters. And this technology will be different over different time points. But this technology may not be different at a particular point of time across the individual units. Okay, so a set of factory units, we are considering a set of factory units producing similar products, suppose pharmaceutical units. So in a pharmaceutical manufacturing units, the level of technology at a particular point of time, that is the level of technology today, may be roughly similar for all factory units. But the level of technology used today may be different from the level of technology used in 2 years back, 3 years back. So in this way, the level of technology may be different for different time points, and we may not have information properly about the level of technology. For that reason, the level of technology or the effect of the technology is unobserved, and as it is unobserved, we safely incorporate into the random error component. So in this decomposition, we assume that the error term is different over time, but not across the cross-section unit. So in this way, we can decompose the error, either allowing one part across the cross-section unit or allowing one part over time. So this type of decomposition is called one-way error decomposition, and we have a model we will mention just now. The model we have will be called the one-way error component model. So when the error component is decomposed in one way, we have one-way error component model, because we are considering here the error component model. So different types of error component model we may have. When we decompose error in one way, we have one-way error component model like this. Or when we decompose the error in two-way, that is, we are considering the both dimensions together along the cross-section unit mu I, as well as along over the time period lambda t. So if uit is equal to mu I plus lambda t plus epsilon it, then we have a model which is known as two-way error component model. So after substituting the value of random error into our regression model in this way, yit is equal to mu I plus xit prime beta plus epsilon it. So earlier mu I plus epsilon it was uit. Now we are considering the decomposed part. Similarly, the second way of decomposition. So either in this form or in this form, we have a model what is known as one-way error component model, because we are considering here decomposition of error in one way. In the first specification, along the cross-section unit, one way, not over time. In the second specification, only over time, not across the cross-section unit. But in the third specification, we are allowing the decomposition both across the cross-section unit as well as over time. So this model is called the two-way error component. Okay, so we have two types of error component. One is two-way error component model, this one, or we have one-way error component model. So if we decompose the error in one way, we have one-way error component. If we have decomposed the error in both way, we have two-way error component model. Now, what would be the nature of the component mu I, lambda t, etc.? Earlier mu I was a part of uit. Now we are decomposing it. We are separating out from the error type. Okay. Now this mu I may be random, may not be random. If we consider this part mu I as a non-random or mu I as a non-stochastic, then we can treat the variation across the cross-section unit in a fixed way, in a fixed manner. But if we consider mu I as a random, we have variation across the cross-section unit in a random way or in a random manner. So depending on the nature of the component mu I, or similarly for lambda t, we have the variation in two forms. One form is called the non-stochastic variation. The cross-section specific or time specific error, that is mu I or lambda t, may be non-stochastic or stochastic. In the case of non-stochastic, if the components are non-stochastic, in that case, the variation across the cross-section unit will be a fixed manner. And in that case, we have a model which is known as fixed effect model. Fixed effect means the cross-section units are different because of the presence of mu I, but mu I is non-random. We are considering the level of intelligence as mu I. So level of intelligence may vary across the cross-section unit in a random way or in a non-random way. So if mu I differs across the cross-section unit in a non-random way, then we will get fixed effect model. But if the level of intelligence vary across the cross-section units in a random way, in that case we have a random effect model. So if the component mu I or lambda t are non-stochastic, we have a fixed effect model, and if the components are stochastic, we have a random effect model. So when normally we can get a fixed effect model, when normally we can get a random effect model, if your panel data is a macro panel. We have defined in our earlier class, there are two types of panel data, If your cross-section unit are a macro unit, then you have a macro panel data. If you have a cross-section unit, micro unit, then you have a micro panel data. So in the case of a macro panel data, the number of cross-section units are limited. Obviously, the number of macro units are limited as compared to the micro. So if you have a macro panel, in that case, your panel data regression model may be fixed effect model. Because in that case, as you are dealing with a fixed number of cross-section units, it is an intuitive explanation, not the proper scientific explanation for the why it is called a fixed effect. Fixed effect means the effect of the cross-section specific behavior is fixed. In other words, the effect is not random. When not random, if we pick up the cross-section units in a non-random way, in that case, the effect will be non-random. So if in your sample data, the number of cross-section units are limited, in that case, you are not picking the cross-section unit in a random way. And in that case, the effect will not be non-random, or the effect will be a fixed, and you will have a fixed effect panel regression model. But in the case of a micro panel data, you have a lot of cross-section units, thousands and lakhs of cross-section units, and the cross-section units will be selected through a random process. And as the cross-section units are selected through a random process, the effect, the variation across the cross-section units may be random. So you will get a random effect model mostly if you have a micro panel data. So if you have a macro panel data, it will be highly likely that your model should be fixed effect. If you have a micro panel data, it will be highly likely that your model will be a random effect model. So in that way, this is a rule of thumb. It is not a proper statistical testing. There are a lot of tests. We are not going into detail now. Testing of hypothesis, we have to decide whether our model will be a fixed effect model, or the random effect model, or the pooled regression model, or the purely unrestricted model. There are a lot of variations. If you have a panel data, you can use different types of model. So what kind of model will be the more appropriate or most appropriate in your data? For that purpose, we have to carry out some statistical tests. And if you go through the standard textbooks, you can find out the different ways how do we carry out the tests. And if you look at, or if you go through my book, in chapter 16 probably, the second chapter on panel data, you can find out the statistical inference or testing with a panel data. So in this chapter, it is discussed in detail how do we decide whether our pooled regression model will be an appropriate one, or the unrestricted is appropriate one, whether the fixed effect model is appropriate one, or the pooled regression is appropriate one, whether random effect is appropriate one, or pooled regression is appropriate one, or whether pooled regression or fixed effect is appropriate one. So there are a lot of statistical tests we can carry out, and we can decide the appropriate model for our data. So we are not discussing the testing of hypothesis because this is out of syllabus for your part. For that reason, we are not going through those parts. But if you are interested, you can go through, because they are discussed in a lucid manner as possible in chapter 16. So in chapter 16, you can find out the different testings of hypothesis in finding out the appropriate model. So whatever may be, in a purely panel data model or in an error component model, there are possibilities of 4 types of error component model. We can divide error component model in one-way error component model and two-way error component model. Again, the nature of the component, error component, that is mu I. Nature of the error component may be stochastic or may be non-stochastic. On the basis of that, we have a fixed effect or random effect. For that reason, there are 4 possible error component models. One is one-way error component fixed effect model. Second one-way error component random effect model. Third one, two-way error component fixed effect model. Fourth one, two-way error component random effect model. So these kind of error component models we can consider in the frame of a panel data. Now let we discuss in short, in a very lucid manner, the first one-way error component fixed effect model. Okay, so let we start with our simple linear regression model like this. Yit is equal to beta naught plus beta 1 xit plus uit. So here y is a scalar, only one variable. X is also a scalar, only one variable. So suppose y denotes wage rate, x denotes level of education, and the other parts affecting level of wage are incorporated within u. Okay, and if we estimate this model with full regression by considering all cross-section units are homogeneous, we have to face an endogeneity problem, and we have discussed how we can get endogeneity problem in a simple linear regression model, that is the full regression model in a panel framework. So for that purpose, we decompose the error part uit in this way. Uit is equal to mu I plus epsilon it. So as we are decomposing the error in one way, our model is one-way error component, and we are considering mu I as a non-stochastic. So we have one-way error component fixed effect model. So why one way? We are decomposing the error in only in one way. And why fixed effect? Because we are assuming mu I is non-random. Mu I is non-stochastic. Although mu I is different for different I, for different cross-section unit, and they are unobserved, but still we assume that they are non-random. So after incorporating this decomposition, you have a model uyit is equal to beta naught plus mu I plus beta 1 xit plus epsilon it. Okay. So in this simple linear regression model, when we decompose the error, mu I term appears in your regression model explicitly. In your original form, there is no mu I, and you can easily apply OLS to find out beta 1 hat, to find out beta naught hat, at least theoretically. Okay, but in this model, if we want to estimate our parameters to be estimated beta naught and beta 1, so to estimate beta 1 and beta naught, we need information on y, we need information on x, along with we need information on mu. So if we have information on mu, we can estimate this model. But what is the character of mu? Mu is unobserved. And as mu is unobserved, we have incorporated mu into the random error part. Okay, so the question is how we can estimate this model with unobserved variable mu I. Try to remember one important point we have mentioned, the advantages of panel data. The most important advantage in using panel data is that it can incorporate unobserved heterogeneity. So if you incorporate some unobserved variable in your model, you can estimate if you have a panel data. In other words, we can estimate this model with panel data, although mu I is unobserved. But we cannot estimate this model where mu I is unobserved with cross-section data or time series data. Okay, so how we can manage it with panel data? So one simple way, if we somehow eliminate mu I from this model, so there will be no problem of appearance of unobserved variables in your model. But we cannot simply eliminate it, we cannot delete it. So we have to eliminate it meaningfully by following some statistical norms. So if we can eliminate mu I from this model by following some statistical norms, then we can estimate this model. So if you have a panel data, if you have more breathing space, you can eliminate mu I from this model. You can eliminate this unobserved fixed effect from this model. And after elimination, you can estimate this model by applying OLS. So how we can follow it? The steps we have to follow in estimating one-way fixed effect error component model is this. So this is our basic model after introducing the error component. Now suppose we are considering mean over time. We can calculate different types of mean if you have a panel data. So we are considering mean over time. Mean over time means calculate mean for each variable along a row, along a column. That is by changing the variable over time, not by a cross section. Okay. So by taking mean value of y over a column, you have y bar I or y bar I dot we have denoted earlier. So y bar I denote the mean value of y for a cross section unit I. Similarly, we can calculate mean value of x for cross section unit I. In other words, in this equation, take sum both sides over time. So the left hand side part, sum of yit, sum over time, sum of beta naught, sum over time, sum of mu I, sum over time. Similarly, we can take sum each and every component of this equation, sum over time, and dividing both sides by capital T. And ultimately you will get this form. So the left hand side, sum of yit divided by t, it indicates y bar I. This part beta naught is constant over time. So sum of beta naught over time means t into beta naught. So after dividing by t, you will get simple beta naught. Similarly for mu I is also constant over time. So you will get t into mu I. So after dividing by t, you have mu I. And for this part, beta 1 is a constant. And from here, you have x bar I. Similarly for the random error, epsilon it. So this is our first equation. We have started with this. So suppose this is our equation 1. We have decomposed the error in equation 2. Okay. We have substitute equation 2 into 1 to get equation 3. Okay. We are taking sum on both sides over time, equation 3, and divide both sides by capital T to get equation 4. Okay. So this formulation is known as between transformation. Okay, between transformation means if we look at equation 4, this equation varies across the cross section unit. That is, this equation is different for different cross section units. That's why this form of the regression model is called the between transformation model. So originally we have this. We have eliminated one dimension, capital T, by taking the average value. Okay. And here the basic assumption that sum of mu I equal to 0. What is mu I? The cross section specific unobserved part. So this part, sum of mu I is equal to 0. This condition is called the normalization condition, because if you look at closely, this mu I part can be looked at as a dummy variable for each cross section unit. Okay, so to avoid the dummy variable trap, we need this kind of restriction. So under this restriction, you will get a meaningful result for equation 3. And the second part, you take a difference. So that is, take equation 3 minus equation 4. So equation 3 minus equation 4. So if we take a difference, 3 and 4, you have this form of the regression model. Left hand side, yit minus y bar I. This is the left hand side. In the right hand side, beta naught will be cancelled out. Mu I will be cancelled out. You have beta 1 into this part plus this minus this part. So this is equation 5. So in equation 5, if you look at, there is no mu I. So mu I is eliminated. But the form of equation 5 is not similar to the form of equation 1. In equation 5, we are considering some transformation. This transformation is called the between transformation, or this transformation is sometimes called the mean corrected form. Okay, so this is the mean corrected form of the model. So now we can estimate this model by applying OLS to get beta 1 hat. This is the value of beta 1 hat, and this beta 1 hat, if you just apply the formula for beta 1 hat for a simple linear regression model. So this part is X, this part is Y. So how do we get beta 1 hat? Beta 1 hat is equal to sum of X into Y divided by sum of X square. Now sum of X into Y indicates the within group covariance, because we are considering within group mean, and divided by sum of X, this part square indicates the variance within group, because we are considering the within group variance. So in this way, we have the beta 1 hat SXYW by SXXW. What is XXYW? We have defined earlier. What is SXXW? We have defined earlier. So in this way, we can calculate beta 1 hat, the estimated coefficient of the regression equation, by considering the cross-section specific heterogeneity, where the heterogeneous factor is non-random. If we consider the error component is a random, that is, we are considering the regression, similar regression equation, similar decomposition, we substitute EYT similarly, but here assume that μ_y is random. In earlier model, μ_y was non-random, and we have got a fixed effect model. If we consider μ_y as a random, we have a one-way error component random effect model. So when we consider μ_i as a random, so μ_i could be taken as together with epsilon IT. Okay, that is, in that case, UIT will be your random error, where UIT consists of two parts, μ_i plus epsilon IT. In our earlier case, UIT is separated out and μ_i is taken as a part of the regressors in the fixed effect model. But in a random effect model, μ_i is to be considered as a part of the random error. Okay, so what would be the appropriate method of estimation of the random effect? We have to look into the behavior of UIT, and the behavior of UIT depends on the behavior of μ_i as well as the behavior of epsilon IT. Why we are talking about behavior of μ_i? Because now we are considering μ_i is also a random. So μ_i as a distribution, as epsilon as a distribution. But in the case of fixed effect, you don't have a distribution for μ_i. Distribution means the probability distribution. Because in a case of fixed effect model, we have considered μ_i as a non-random. So for a non-random variable, you don't have any probability distribution. So when we consider μ_i as a random, we have a probability distribution of μ_i, we have a probability distribution of epsilon, and ultimately the probability distribution of U depends on the distribution of μ_i and epsilon. Now let me assume the randomness of μ_i in this way. So μ_i is a random. So μ_i follows some distribution, and its mean value is 0. Expected value of μ_i is equal to 0. And this condition is similar to the normalization condition we have mentioned earlier. So this condition is similar to the condition of the 0 mean. Mean value of the error is 0. So what is the basic implication of this assumption? Mean value of the mean value of this component is 0. So in your sample, suppose you have a lot of workers, and μ_i denotes the level of intelligence of the workers. So some worker is more intelligent, some worker will be less intelligent. So if we take the mean intelligence will be 0. So we can normalize the level of intelligence as 0 on average sense. Okay. And variance of μ_i, sigma square mu is considered as a constant. Covariance of mu in and x is a regressors we are using the model. So x and mu are not correlated. μ_i, μ_j is 0. That is, mu are also not correlated. So these are the assumptions on the distribution of μ_i. Similarly, the assumption of distribution of epsilon is similar as in the case of normally use the disturbance in a linear regression model, the 0 mean assumption. constant variance assumption, zero correlation assumption. So under those assumptions, we can look at the behavior of the error we have in the model. So our original error is UIT. So if we incorporate these behavior, the components of the error mu I and epsilon it into UI, you will get easily the expected value of UI equal to 0. Variance of UIT is equal to constant sum of sigma square mu plus sigma square epsilon, that the sum of the variance of the two components. But the covariance of UI Uj will be different. If you calculate the covariance term for classical linear regression model, this covariance should be 0. But in this our setup, by separating out mu I and epsilon it, we can see that the covariance of UI T and UJS will not be always 0. It will be 0 only when this case, only under this case, that is for all I not equal to J, T not equal to S. But this covariance will not be 0 here. So the covariance component, that is the zero covariance or non-autocorrelation, this assumption is not appropriate for the random effect model. For that reason, the random effect model cannot be estimated by applying OLS. So in that case, we have to follow a model what is known as the GLS, generalized least square. So generalized least square is nothing but the general form of the least square model, where we have to manipulate the variables in a way such that we have got the covariance component always equal to 0. Okay. In this case, covariance component is not always 0, and it creates a lot of problem in the OLS estimates. For that reason, our task will be to make this covariance is 0. So we can transform the variable y, we can transform the variable x in such a manner that the covariance of the random error UIT UJS becomes 0, and after that we can apply OLS. This is the method for GLS. So this is in a simple way we can look at the one-way error component random effect model. Okay.